Okay, in this lesson we're into Unit 7, Chapter 7, Exponential Functions again. We're looking now at transformations of exponential functions. We're going to look specifically at the effects of the parameters a, b, h, and k have on the graph of the f of x equals a times c to the b outside of x subtract h plus k. So these four variables or parameters, how they affect the graph of the function. Okay, so we're going to focus specifically on here from Section 7.2, applying translations, stretches, and reflections to the graph of exponential functions. And we're going to be representing these transformations in the equations of exponential functions. Let's do that. First of all, we're going to review all four parameters and what they actually do to the graph of the function that we start with. The graph of the function of the form f of x equals a times c to the power of b outside of x subtract h plus k is obtained by applying transformations to the graph of the base function y equals c to the x, where c is greater than 0. Now we know that c could be between 0 and 1 or greater than 0. We're only going to be doing transformations of functions where c is greater than 0. Let's have a look at the first parameter, the a in this function. What does that do to the graph of the function y equals c to the power of x? The a represents a vertical stretch. And it's a vertical stretch of a factor of the absolute value of a. Now the reason why we take the absolute value, of course, is because vertical stretch is always positive. If a is negative, that indicates a reflection in the x-axis. But vertical stretch is always positive. So if we were to take a couple of examples here, if we were to take the function y equals 3 to the power of x, for example, and we place a 4 in front of the 3 to the power of x, we've stretched the graph by a factor of 4. That's a vertical stretch of 4. And you can see that the point 0, 1 is now mapped to the point 0, 4, stretched by a factor of 4. The mapping rule for that function is xy maps to x comma ay, vertical stretch of a. Note again that if a is less than 0, it's a reflection in the x-axis. If you look at this example here, the graph of y equals 3 to the x is reflected in the x-axis, indicated by the negative, but it's also stretched by a factor of 2. So if we were to take this graph and reflect it in the x-axis, of course the y-intercept of 0, 1 will become 0, negative 1, but then we stretch it by a factor of 2 afterwards. Remember RST, whenever you construct graphs, you do your reflections, then stretches, then translations. What about the parameter b? B represents the horizontal stretch. Now in this particular case, the horizontal stretch is 1 over the absolute value of b. The vertical stretch is a, but the horizontal stretch is 1 over b. Again, if b is less than 0, it indicates a reflection in the y-axis this time. If a is less than 0, it's a reflection in the x-axis. If b is less than 0, it's a reflection in the y-axis. Here again are a couple of examples. Let's take the function y equals 2 to the power of x as our base function. The graph of y equals 2 to the 3x indicates a horizontal stretch of 1/3. This graph has been stretched. The original graph has been stretched by a factor of 1/3 to produce this new red graph. Stretched by a factor of 1/3. If you look at the other example here, y equals 2 to the negative 1/2 x. Y equals 2 to the negative 1/2 x. This particular graph is now reflected again in the y-axis because of the negative here. So you take the graph of y equals 2 to the x and you reflect it, but it's also stretched by a factor of 2. Stretched by a factor of 2, and it's a horizontal stretch of 2 in this case. A horizontal stretch of 2. Because again, the horizontal stretch is 1 over the absolute value of b. Horizontal stretch, again, is always positive, just like vertical stretch is always positive. But you take the reciprocal of b to determine the horizontal stretch. You don't take the reciprocal of a to determine the vertical stretch. So there's a and b. Let's have a look at the parameter k. The value of k represents a vertical translation of the graph up or down. Again, if you look at the mapping rule, it's x comma y plus k. I've sort of forgot the mapping rule in the last one. Let's go back and look at it quickly. The mapping rule for the horizontal stretch is x, y maps to x over b comma y. X over b comma y, or 1 over b times x comma y. Same thing. Because again, the horizontal stretch is 1 over b. Vertical stretch indicated by the value of k. Let's again look at an example. Y equals 4 to the power of x. There's my base function. If I do y equals 4 to the power of x plus 2, it takes the graph and it moves it vertically 2 units up. Notice that the horizontal asymptote of y equals 0 now becomes the horizontal asymptote of y equals 2. The same is true if you were to take the graph and move it down 3 units, like is indicated with this graph. Y equals 4 to the x subtract 3. It simply takes the entire graph and moves it down vertically 3 units. In that case, of course, the horizontal asymptote will also move, and the horizontal asymptote becomes the line y equals -3. Again, your mapping rule becomes x comma y plus k. Notice again, the sign of the k doesn't change here. It remains y plus k. Just like the value of a didn't change in your mapping rule. So these two remain unchanged, a and k. Unchanged in the mapping rule. And you're going to see some examples of that shortly. And the last parameter that we need to consider is the value of h. Up right here, the value of h. H represents a horizontal translation, left or right. If h is positive, in other words, you get something like x subtract 2, then it's a horizontal translation to the right. Here's an example. Y equals 6 to the power of x. There's your base function. Y equals 6 to the power of x subtract 3 will take the graph and move the graph 3 units to the right. Y equals 6 to the x plus 2 will take the graph of y equals 6 to the x and move it 2 units to the left. Again, if you look at your mapping rule, it's x, y maps to x plus h comma y. Notice that you sort of take the opposite of what you see in the brackets here to put in your mapping rule, just as you take the reciprocal of b for your mapping rule. So these things here change in your mapping rule. These two remain unchanged in the mapping rule. So just keep that in mind. Some other things that might be of interest and a few things you might want to remember regarding the equation that you see here. Y equals k represents the horizontal asymptote. And you just saw that a minute ago. That if I move the graph up k units, the horizontal asymptote is k. If I move it down k units, the horizontal asymptote is y equals -k. Depending on what the value of k is, will represent the horizontal asymptote. If a is positive, the range of the function is going to be y is greater than k. What's important here is that there's only two things that will affect the range of this function, and that's a and k. These are the only two things that affect range. Now remember, your domain is all real numbers anyway. But these are the only two things that affect the range. So if you're wondering how to find the range of an exponential function, you don't need to consider the b, you don't need to consider the h. All you need to consider are a and k. If a is greater than 0, meaning that there's no reflection now in the y-axis, x-axis, sorry, no reflection in the x-axis. So the range is simply going to be y is greater than k, because that's your vertical asymptote. The graphs move vertically k units. If a is less than 0, then you do get a reflection in the x-axis, and the range is going to be y is less than k. Quick way to remember range. Simply remember this here. Of course, your mapping rule for the entire function is x, y maps to 1 over x plus h, a, y plus k. Again, notice that I've taken the reciprocal of b to get 1 over b. I take the opposite of the x plus h to get x minus h. I keep the a as it is, and it's ay plus k. I keep the k as it is. Whatever sign you see here goes in your mapping rule. Another thing that might be of interest here, and that is whether or not it's a decreasing function depends upon really your exponent and also your base. If the base is greater than 1, if c is greater than 1, and if b is positive, it remains an increasing function. However, if the base c is greater than 1 and b is less than 0 or negative, it actually becomes a decreasing function. And that should make perfectly good sense, because if you were to think about a function, for example, and I'll just create one here just to make it clear. If you were to take a function which is a growth function like this, where c is greater than 1, of course, y equals c to the x, where c is greater than 1, that's what a growth function looks like. And if I were to make b negative, as soon as I make the value of b less than 0, then I get a reflection in the y-axis. As soon as I take that graph and reflect it in the y-axis, where b is 0, it now becomes a decreasing function. Notice again where b is less than 0 and c is still greater than 1. It's a decreasing function now because of the reflection. And the same is true that if you started with a decreasing function, for example, one like this, and I'll quickly do this here. If we start with a decreasing function, give me a second here, I just use a different color, like this. This is a decreasing function, y equals c to the x, where c is between 0 and 1. If b is greater than 0, no reflection, it's a decreasing function. But if b is less than 0, if b is less than 0, then again we will get a reflection in the y-axis. If I take that graph and reflect it in the y-axis, it now becomes an increasing function. So this particular function might look like y equals c to the x, sorry, c equals b to the x, if b could be less than 0, but yet c be between 0 and 1, and you can see that it becomes a growth function or an increasing function in that scenario. So again, this reflection really impacts whether or not it's going to be an increasing or decreasing function. If there's a reflection here, it's the opposite of what you think it is. So normally you simply look at the base to determine if it's increasing or decreasing, not anymore. You need to look at the base and you need to look at the value of b. It's going to be increasing if b is positive and if c is greater than 1. If c is positive, but yet b is less than 0, it actually becomes a decreasing function due to the reflection. And the same is true with your decreasing function becomes an increasing function with the reflection. Okay, let's have a look at some examples now of transformations here. Again, it might be a good idea for you to pause these recordings as we attempt to do these questions and try them on your own first, and then continue the recording and listen to how I actually do the solution. Okay, what is the equation of the horizontal asymptote for this particular function? Y plus 2 equals 4 times 3 to the power of x. Again, if you want to pause the recording, go ahead and do that. Okay, I'll answer the question. Y equals 4 times 3 to the power of x, subtract 2. I'm going to rewrite this in what we call functional form, meaning solve for y, and the equation will look like this. You should remember what we just did, whereby this value here of k represents the horizontal asymptote. This is the graph of y equals 3 to the x, moved down 2 units. There's a vertical translation of negative 2 here. So imagine taking the graph of y equals 3 to the x and moving it down 2 units and stretching it by a factor of 4. So if I move it down 2 units, then my horizontal asymptote will become the line y equals negative 2. Again, the original function is a growth function. You stretch it, but more importantly, you move it down 2 units. As soon as I take the graph and I move it down 2 units, then my horizontal asymptote becomes the line y equals negative 2, rather than y equals 0. So the value of k represents the horizontal asymptote. In this case, k is equal to negative 2. Next example, which mapping rule transforms the graph of y equals 1/5 to the x onto y subtract 2 equals 1/5 to the 4x plus 8. Now again, the 1/5 has nothing to do with the transformation. The 1/5 is the base of the function. That's all it is. It's a function of the form y equals 1/5 to the power of x, where c is 1/5. That's all. It's originally a decay function. That's all it means. So we need to create the mapping rule for this function. Again, if you want to try that, by all means do so, but I will continue to do the solution. I'm going to rewrite my exponent with a set of brackets. You need to do that. 4 outside of x plus 2. I'm going to bring the 2 over and say plus 2. Again, the 1/5 has nothing to do with the transformations here. It's the base function that's being translated. What we need to consider are the values that you see here. 4, 2, and this 2. Notice how I rewrote that as 4 inside of x plus 2. You need to do that in order to determine the mapping rule. Now, if you look at the 4 options, you should be able to directly go from your equation right into your mapping rule here. Remember I told you that the exponent here, you take the opposite and the reciprocal of everything that you see here. So the 4 becomes a 1/4. So that narrows it down to A, B, or C. The x plus 2 becomes an x minus 2. My answer has to be B now. And of course, the plus 2 here doesn't change in the mapping rule. It becomes y plus 2. So that is the correct answer of B. Remember I said that you take the reciprocal of the 4 in the mapping rule. The x plus 2 becomes an x minus 2. This doesn't change, and the value of A doesn't change. The value of A here is still 1, which is actually in front of the y there. Example 3. What is the resulting equation when the graph of y equals 4 to the x has a horizontal reflection in the y-axis, is vertically stretched by a factor of 1/2, and is translated horizontally 1 unit to the right? Again, you might want to pause the recording to try this one before we proceed. Okay, the first thing you might want to consider here is rewriting each equation in the form y equals. So I would rewrite this as y equals, get rid of the -2 by multiplying both sides by -1/2. So I have -1/2 times 4 to the x subtract 1. Here will be y equals -1/2 times 4 to the x plus 1. The third one here would be y equals 1/2 times 4 to the negative x subtract 1. Very important that you take that negative out. To put it in true transformational form here, I'd have to take the -1 outside of x subtract 1. Sorry, take the negative outside of this to get negative inside of x plus 1. Negative x subtract 1 is what you see here. You've got to write that set of brackets there. If there's anything at all in front of the x, including a -1, you do need to remove it as a common factor. Very important. And the last equation, I would write it as y equals 1/2 times 4. Again, look at your exponent. Remove the -1 outside of x subtract 1. Okay, let's see what we're looking for here. We're looking for a horizontal reflection in the y-axis. If there's a reflection in the y-axis, you would see a negative in your exponent right here. A reflection in the x-axis would result with a negative right here. The way I remember that is this. If there's a reflection in the y-axis, the negative's in front of the x. If there's a reflection in the x-axis, the negative's in front of the y. See how it started here in front of the y, although now it's over here, but it's not in front of the x. That's all I remember. It's just the opposite, you see. So I'm looking for a reflection of the y-axis, so I'm looking for a negative out in front of the x here. That's what I see. So these are my two possibilities right now. So I've narrowed it down to B and C or D because of the very first condition. It's been vertically stretched by a factor of 1/2. Both of these are stretched by a factor of 1/2, so that doesn't help me. I know it's C or D already. That doesn't help me because both have a vertical stretch of 1/2. And it's translated 1 unit to the right. A translation of 1 unit to the right would result with x subtract 1. Horizontal translation, in this case, is +1. The vertical stretch is indeed 1/2. And again, there is your reflection in the y-axis. So the correct answer is D. So we'll look at another example here. Which graph represents the function y equals a times b to the cx, where a is greater than 0, b is between 0 and 1, and c is less than 0? What I would do in this case is I would I would consider an example whereby I would choose values of A, B, and C, plug into my equation, and from there determine what the graph should look like. Let me show you what I mean. I got y equals A times B to the cx. Now normally we see that as A times C to the bx, but in this particular case, the B and C are switched. That shouldn't really have an impact on you here, okay? A is greater than 0, so A is positive. So let's make A 1. It's as good as anything. So I'm choosing values for A, B, and C. B is between 0 and 1, so I'll choose a half. And C is less than 0, like maybe negative 1. There you go. So I've chosen values of A, B, and C, and I've created an equation. Now I'm going to look for the graph that best matches that equation. So let's look at what transformations are occurring here. If I want to consider the graph of the function, I need to consider transformations in a certain order. RST, reflections, stretches, and translations in that order. The base function here is the function y equals 1/2 to the power of x. What you see in the brackets here is just your base function. So I know that I'm actually translating an exponential function that is a decay function. Here's what the function looks like initially. X and y. So it's a base function of y equals 1/2 to the power of x. There's an example. It's a decay function. Now what am I doing to the decay function? Well, the only thing that really has happened here is I've given it a reflection. I've reflected the graph in the y-axis. So imagine taking this graph and reflecting it in the y-axis, and the graph would now look like this. So which of these 4 graphs best or most closely match the pink one that I just drew? The answer is C. That, to me, is the best way to do these types of questions, is actually choose values for A, B, and C, plug them in, and then do your translations. RST in the order in which they should appear, and we're done. Answer C. Example 5. What is the range of the function? Now note the way this function is written in what we call transformational form. I'm going to put it back in functional form because most of the work that we've been doing is in functional form. So I'm going to rewrite this function by solving it for y. First thing I have to do is get rid of the -3 here. So I'm going to multiply both sides by -1/3. So imagine multiplying this side by -1/3, multiplying this side by -1/3. I will be left with y plus 1 equals -1/3 times 5 to the x subtract 2. I bring the 1 over, and I get subtract 1. Now some of you may have learned how to deal with this in transformational form rather than in functional form. And that's fine. If you can do the mapping rule or whatever you need to do in this form, you go ahead and do that. I'm going to be doing it in this form here. Now, I'm not sure if you recall what I covered earlier, but I said that the only 2 things that affect range are the values of A and the values of K. The exponent here will not affect your range. It doesn't matter what you do with the graph horizontally. If you move it left or right, or if you stretch it, it will not affect the range. You think about that. I can stretch the graph horizontally as much as I like. I can move it left or right. The range will not be affected. The only thing that affects range are A and K. Okay, so we need to think about what's happening to the graph of this function. I would think about this function. Now you may remember what I did earlier, whereby, it's a very simple method of, if A is less than 0, then, the range is going to be less than K. If A is greater than 0, it's going to be greater than K. I think I'd rather try and memorize that. Rather than memorize that, I think I would rather try and picture what happens to the graph. So I'm going to think about this graph again. Let me try and make this a better line here. I'm going to try and picture what happens to the graph in order to get my range. I like getting range from a graph. What do I have? I get a base function of y equals 5 to the power of x. So it's a growth function. Y equals 5 to the power of x. Now the only 2 things I need to consider are the value of A and the value of K. And in actual fact, the amount at which the graph is stretched really doesn't impact the range either, but the reflection will. So whether or not there's a reflection and whether or not there's a vertical translation will affect your graph. We see that we do have a reflection, and the reflection is in the x-axis, and that's what really affects your graph, if there's a reflection in the x-axis. So if I take this graph and reflect it in the x-axis, and let's stretch it by a factor of a third as well, okay, so it looks something like that. So I've done my reflection, I've done my stretch. Now I need to take the graph and I need to give it my vertical translation of -1. So now when I produce my new graph, I'm going to produce a graph whereby the graph is going to be moved vertically 1 unit down. So if I take this graph now and I move it down 1 unit, it's going to look something like this. And remember now, I moved it down 1 unit, so y was equal to -1. So the question, of course, is simply, what is the range of that graph? So I sketched the graph, you see, because I knew what my base function was, y equals 5 to the power of x. I knew I had a reflection and a vertical stretch, so I did that pretty quickly there. And then I gave it a vertical translation. The vertical stretch doesn't impact it. It's the reflection and the vertical translation. So I reflected in the x-axis, I moved it down 1 unit. The range of this graph is going to be values of y such that y is less than -1. Y such that y is less than -1. That's how I personally would do this question. Now again, if you want to memorize what I covered earlier, I'll go back to it. Right here. If a is greater than 0, the range is going to be y is greater than k. If a is less than 0, the range is y is less than k. That's exactly what I had over here. A was less than 0, the range was y was less than k. K is -1. Y is less than -1. But I think it's important you understand why that is the case, and hopefully I've explained that there. Okay, and one more example here, I think, and maybe two. Let's see what we have. Which function represents the graph of 1/4 outside of y plus 3 equals 1/2 to the -x? So again, you want to think about your base function. You want to think about the transformations that are occurring. Try to identify the correct graph. And again, you need to think about RST in order to do this. I would do it like this. I would think about my original graph, which is a function y equals 1/2 to the power of x. So it's a decay function to start with. Looks like that. There's my base function. Now what have I done to that function? Are there any reflections? And the answer is yes. I have a reflection right here. The negative in front of the x is a reflection in the y-axis. So I'm going to produce that reflection first. So here's my reflection. What else do I have here? Well, if you want to put it in functional form, I suppose, it would look like this. Y is equal to 4 times 1/2 to the -x subtract 3. And I pretty quickly did both here, whereby I got the y by itself by getting the 1/4 to the other side by multiplying both sides by 4, and then I simply brought over 3 and called it -3. So I've got my reflection done. Stretches. It's stretched by a factor of 4, and it's stretched vertically by a factor of 4. So if I stretch it vertically by a factor of 4, I will get a graph that's going to look something like this now. That's all it does, is stretches it by a factor of 4. Because I'm only trying to figure out what the graph will look like. And then what do? I move it down 3 units. So now I'm going to get the graph a vertical translation of 3 units down. And by doing that, I create a horizontal asymptote of y equals -3. And when I move it down 3 units, my new graph is going to look something like, well, something like that, I suppose. It's been an ugly sketch, but you get the idea. The correct answer is B, isn't it? That's the only one there that's even close to what I just sketched. So the correct answer has to be B. So again, I would do these by considering RST in that order. Do all the translations in the correct order, and you should get some idea what the graph looks like. I think this is the final example here. Which function represents exponential growth? which is an exponential growth function. Now again, with this one, you need to consider the value of c, which is your base here, and you need to consider your exponent and whether or not there's a reflection. Again, you might want to try this one first before I do it. We're looking for an exponential growth function, or an increasing function, whatever you want to call it. Well, this particular function has a value of c between 0 and 1, so it starts out as a decay function. There is no reflection. There is no reflection in the y-axis. So if there's no reflection in the y-axis, then my decay function stays a decay function. So that's a decay function. This one starts out as a growth function. So think about it as a growth function because the value of the value of c is greater than 1. So it starts out as a growth function. And the fact that you got a reflection in the y-axis right here would result in the function becoming a decay function. So the function would look like that after you create your reflection. So the answer is not A, the answer is not B. C. The value of C is between 0 and 1, right? Because 4 over 5 is between 0 and 1. So we're starting out as a decay function. And now you can see that there is also reflection in the y-axis. So if I took this graph and I reflected it in the y-axis, I would now create a growth function. The correct answer is C. Okay, summary of key ideas here very quickly. To sketch the graph of exponential functions of the form that you see here, you apply transformations to the graph of y equals c to the x, where c is greater than 0. Again, we looked at some examples here where c was between 0 and 1, but that's okay, I guess. The transformations represented by a and b may be applied in any order before the transformations by h and k. As I said, you're going to do your stretches before you do your translations. The parameters a, b, h, and k in the exponential function of the form that you see here corresponds to the following translations. Again, just a quick review here. A is the vertical stretch. If a is less than 0, there's a reflection in the x-axis. B corresponds to the horizontal stretch, and it represents a horizontal stretch of 1 over b. And if b is less than 0, we get a reflection in the y-axis. And h, again, represents a horizontal translation to the left or right, depending if h is positive or not. And k represents a vertical translation up or down. If k is positive, it's up. If k is negative, it's down. And that ends this particular lesson on transformations of exponential functions.